Hey guys, this is your next set of notes for Unit 6. Today we're talking about phase changes and heat. Make sure that you are filling in the notes as we go. So how do we calculate the energy to change the phase of a substance or to heat it up, which means to change its temperature? Those are the things we're going to be talking about today. Remember that it's going to take energy to heat anything up. For a pure substance that doesn't change phases, we can calculate how much energy is needed using this equation. That is Q equals mc delta T. Q is the energy, that's calculated in joules. M is mass. C is specific heat capacity. And then delta T is just going to be your change in your temperature, which is your final minus your initial. Again, remember, if something is cooling down, then it's releasing energy. So we can look at this little chart and see that temperature on the left is going up, and then obviously time as you go across this x-axis. In the 1, the 3, and the 5, that's the only time there's a change in temperature according to this graph. That's something that we can calculate. That's why those calculations are only in those areas. On 2 and 4, there's no change in that line. That line is straight across the x-axis, which means that there wasn't a temperature change, so not really anything to calculate at that point. So again, that's because temperature is not changing on 2 and 4. So how do we calculate the amount of energy required during a phase change? Well, there's a couple different things you need to know. We have HF, which is the heat of fusion. So Q, energy, is mass times HF. And then we have HV, which is heat of vaporization. And again, Q equals mass times the heat of vaporization. We use one of these two constants instead of specific heat and delta T because there's no change in temperature on that 2 and the 4 on that graph that we were just looking at. Think of HF and HV as your specific heat, or C. So then I can plug in those equations on 2 and 4. I don't have my delta T on 2 and 4 because there's no change in temperature. So how do we calculate the amount of energy? So again, heat of fusion is going to be the amount of energy required to change 1 gram of pure substance from solid to liquid at its melting point, meaning I'm not changing the temperature. This is a physical constant. Heat of vaporization is the amount of energy required to convert 1 gram of pure substance from liquid to gas at its boiling point, meaning again, you're not changing the temperature. So here's some important constants. We have the heat of fusion for ice. We have heat of vaporization for water, specific heat of water, specific heat of ice, specific heat of steam. Those are things that you can write down for a test. You don't have to memorize those. Let's go back one. How much heat is absorbed when 10 grams of ice melts at 0 degrees Celsius? Okay, so my heat absorbed is my mass times my heat of fusion, which is a constant number from that last page. So this is ice melting. So if I go back to this constant, I'm using the heat of fusion for ice, which was that first number, the 334. Okay, so all I need to do is multiply 334 times my mass, which was 10. Multiply those two together to get energy. So it was 3340 joules. Where does this energy go if the substance is not increasing in temperature? So we're adding heat energy. The energy goes into changing the shape or potential energy of the molecules. It's breaking their attractions apart to alter the shape. There's no more energy after that point, so that's why the temperature doesn't change. How much energy does it take to vaporize 10 grams of water? So let's go back. We're looking at vaporizing. Oops. Heat of vaporization for water, 2270. So I can multiply 2270, which I think I have a typo, times 10 grams, and multiply those and get the answer. So the energy goes into changing the shape or potential energy of the molecules, just like on the last slide. It's breaking the attractions apart to alter the shape. After that happens, there's not enough energy left to increase that temperature at all. It takes a lot more energy to go from a liquid to a gas than from a solid to a liquid. So a liquid to a gas, then a solid to a liquid. Why? So here I have water changing from liquid to gas, and it requires 22,600 joules per gram. And here I have water changing from solid to liquid, which requires 3340 joules per grams. There's more energy required to change a gram of water from a liquid to a gas because all of those particles have to be separated, and they have to be separated from a greater distance apart. Okay, here is a heating curve of water that I just want you to see. In the bottom corner, it says it's -25 all the way up to 0. That's going to be ice. 0 is also the melting point for water. So as I go up from 0 to 100, that's when it's in the liquid phase, water. Once I hit 100, that's the boiling point. So from there, it's going to turn into a gas. Anything above 100 is going to be a vapor. So this is just a curve of all those important points of water. Okay, let's do an example. I have 795 grams of ice in my freezer. The water in my house is not working, so I need the ice for making spaghetti. The ice is at -25 degrees Celsius. Calculate how much energy it takes to completely boil all the ice into steam at 115 degrees Celsius. And how many steps is this? So if we looked at that heating curve, if I'm going all the way from -25 all the way up to 115, that is 5 steps. Because I showed you the heating curve of water, it has to thaw out, and then it's in the water phase, and then it has to heat up and boil, so then it's in the gas phase, and then from there, it's getting hotter and it's just turning into vapor. So that's going to be 5 steps. Make sure you fill that in on your paper. So I have the heat from the ice, which is your -25 to 0. Then I melt the ice. Then I have heat the ice from 0 to 100. Then boil the water that's there. Heat the steam from 100 to 115. That is why it's 5 steps. So that means I have 5 separate equations that I need to look at to calculate energy. This is going to be a different equation in each section because I have a different physical state of matter. I have solid, liquid, gas, and then on 2 and 4, I have a time when it's not changing temperature, but it is changing energy. So here's these constants again. You're going to need these to plug in. A lot of this I've already done for you on your notes, so just pay attention. Here's the 5 steps. So all I've done is plug in numbers. In the first column, I have mass, 795 grams. In the second column, I have some of my constant numbers. Also have on 2 and 4, either heat of fusion or heat of vaporization. Those are the numbers that were in the last slide that I showed you. The 2.01 and the 4.184, those are your specific heats for either ice or for water or for steam. And then I also have temperatures plugged in if there was a change in temperature. So when you do all that math for each one, you get these numbers. Make sure you copy these down if they're not already. And then you should add them up to get a total. If it's in joules, it would be 2,466,726 joules. If you ever needed to convert that to kilojoules, you could do that as well. So lots of steps, lots of math. Remember that you can have any phase change diagram for any substance to do these heat problems. It's not just water, so you could really look these up for any substance. This one's not water because I know that water is not at -50. This is actually gonna be for gold. So these are your melting points and boiling points for gold. Again, you can always look these up for any element if you ever needed them. So for today, I actually don't want you to do these practice problems right now unless you want to. You can try and get ahead. It's pretty much just using the same constants that we were doing in the notes. I do want to make sure that you filled in your notes for this lecture, and I want to make sure that you finished your gas law practice problems from last week. If you need extra help with those, I have posted some helpful hints in Google Classroom.